they have them in the hall. Yeah.
Mine is like it's small, but it's just it's not built to like take turns and super fast. Yeah. You made a minivan.
Alrighty. All right, well, it's start time, so we better get started here, whatever we are, the second week, second day. And same kind of little warning I gave you before. We're working kind of quickly through these 3 chapters, trying to hit a chapter a week, and I mean a chapter a day instead of a chapter a week, as we're kind of used to, and as what we will normally do. And so we did 16, actually to a fuller extent than I even expected, so that was good, and that gave me some encouragement for today. So I'm thinking today we will hit 17 with everything covered, and maybe a little quick, and I'll kind of play that same game. One equation I will say, well, your author does a good derivation for you, so I'll leave you to that. The other equation, though, it's probably important I do work at. I was thinking about that all morning long, going, it'd save a lot of time if I didn't, but I don't think you'll really understand the equation unless that one is worked out, and so I think that is better if I do that. So that's where we're headed, trying to get all of 17. It can go hopefully quite successful and quickly if we just remember that sound waves are an application of the waves we learned in general. So frequencies, periods, amplitudes, x plus or minus vt for the equation, the wave equation, you know, all those things that we learned in the last chapter, or maybe you're doing and working on now in chapter 16, we're going to start applying them to 17. So that's kind of the short explanation. Is we're going, let's apply our general information of waves that we just learned on Tuesday together with a specific type of wave, sound waves. And so that's where we begin. That's the title. Here's chapter 17, sound waves. First question, what are sound waves? Well, here's probably the best visual example I can give you, is if I take these rods, and of course these are rods, but if you kind of think of them as little spheres floating in the air, so that's why we put these little stickers. I don't know if you can kind of see the little fluorescent sticker there. But if you could imagine I'm coming along and I hit the first little sphere, what does it do? Hits the second, right? Now the first one stops, second one moves. Second one hits the third, second one stops, third one moves. Third one hits the fourth. Fourth one moves, third one stops, so forth and so on, right? And so it hits, and here's my question. Does the energy get transmitted down to here? Did the material get transmitted? No. So we call this a wave, right? And so this, it would be an example of a wave because we said a wave was when the energy got transmitted, but not the material itself. And so we can see these visually with our eyes. But the mental picture I want you to have is the same thing would go on with all the molecules that are in the air. These little tiny molecules, mostly nitrogen. If one nitrogen atom is hit, or a group of them are hit by my fist, if I hit them, they hit the next, they hit the next, they hit the next. If there's a bunch of them right here above the table and I hit them, they go out, hitting the next, hitting the next. Now you don't see that, but did you hear it? See, because what happened is that hitting, and eventually hit your eardrum. And that's what a sound wave is. And that's the visual picture I want you to have. The short answer here really is that what we have for sound waves is the movement or the oscillation of the atoms. They are what we called in the last chapter waves, where the vibration is in the direction of their movement, and so they are longitudinal waves. And so again, good example is, there it is. A picture might be something like this. If I take a piece of metal, we'll call it a tuning fork here, and I hit it with a rubber mallet, can you hear it? Yeah. Why? What physically is happening? Yeah, if I was kind of drawing a picture, here's the piece of metal. I hit it, making the metal piece, and this side too, but I won't focus my attention on that side. But as I strike it, these metal pieces are going to be moving back and forth. And as they move back and forth, it would look something like this. This metal piece would come back and then hit a bunch of molecules. And so I will kind of draw a cluster of molecules here, all grouped together. And it just kind of slammed the bunch together. But of course, those do what? Hit the next, which then hit the next. And so it looks kind of like that. And this group then moves along. And so this group hitting the next, hitting the next, hitting the next may end up right here a little bit later, right? Now I say a little bit later because at that same time, while this is moving on to here, what is going to happen with this tuning fork? Exactly, that piece of metal is going to come back and hit it again. And then another big clump. So this big clump that has gone on to here is now followed a little bit later by an identical clump. A pattern that repeats itself. What would the wavelength be here? Well, from clump to clump, right? And then of course this all happens a third time. As this goes back, this original clump that has now traveled to here would now be here. The second one has now traveled to here, and then it makes a third one. And I'll stop drawing there. I think you get the idea here that this is just going to keep and continue on and on and on. And so there is step one of the chapter. What really is a sound wave? And it really is just the oscillations of the molecule. It is a longitudinal wave. Now, I should emphasize this. Could this happen underwater?
It works better underwater.
All right, so it can, right? So can you have sound waves underwater? Yeah. Could it happen inside a solid material?
Even better.
Like a block of aluminum, concrete? Yep. And sound waves are in there too. So please don't fall into the trap thinking that the sound waves have to be in the air, because that's mostly what we're used to. Fortunately, many of you have probably heard sounds underwater, so that doesn't really surprise you either. But the solid, I don't know if our ears have ever been in a solid here. But if you've ever had your ear laying down on a tabletop and having somebody tap on the table, or listening to maybe some loose parts or some breaking parts or a bearing that's out of balance on a car, you know, there's a sound to it, a sound that transfers through the solid material. If you've ever had a sonogram, maybe because of kidney stones or a pregnancy, you know, there's these sound waves that travel through that material, in this case the human body, and there's a reflection off of it. And so the sound waves are just waves, just like light waves. I guess another good example is the navigation of a submarine. I mean, how does a submarine know, here's a canyon I can drive through, here's the end of the canyon, here's a mountain. I mean, does the submarine have a window with headlights sticking out the side? I mean, that's how you would drive a car or fly an airplane. We use the reflection of the light waves. But you could just as well use the reflection of the sound waves and the pattern of the sound waves. Bats are really good examples of that. You know, they fly at night. They have where they're going is quite fascinating to me. Flying around in a cave, not crashing into anything, hunting a little moth, getting the reflection of the sound waves and knowing that this is a moth and knowing where the moth is going and to snatch it out of the air, I find amazing because my ability to catch and to figure out where things by sound don't work quite like that. My eyes do. You know, I can follow the moth really well. I'm not sure I could catch the moth, you know, but I could get an idea. I don't crash into the walls. I can go out that door and around the building. And so using my eyes for navigation makes a lot of sense to me. I've got no problem with that. But sound is the same thing. And so the dolphin, the bat, would
it go through the center of an incandescent light bulb?
Would what go through the center? Sure, sure.
Isn't it in a vacuum?
Oh, no, incandescent bulbs aren't vacuums anymore. The original ones, you know, because that was the discovery of the light bulb. I mean, everybody knew that you pass electricity through a wire, it gets hot, it gives off lights.
I mean,
But the real key, right, was when Edison evacuated the tube, because what happened, nobody really knew, is when you heated it up, that hot element was oxidizing with the oxygen and then burning out. So you put electricity, it gave off light for a moment and then it was gone. And it was Edison who realized, hey, it's the oxygen, and so if he evacuated it, the bulb would last for months and months. And so, but no, today's bulbs have, they just get rid of all the oxygen. They're usually just pure nitrogen.
And so what if it was a vacuum?
Oh, okay, then you wouldn't have sound waves. Right, you can't have sound waves without vacuum. Right, sure, sure. Yeah. Years ago when I worked for McDonnell Douglas, we had a great test. We'd bring in the old DC-10 parts, you'd disassemble them, put them in a big hanger and mount them. Oh, I better tell the story quick. And to look at the structure of it and to see if there was any, you know, micro cracks in it, we would have these huge jets of water, if you can imagine, like two hoses, thin beams, if you will, and you would shoot, like you had the tail, and you'd shoot on one side and you'd shoot at the other, and then we would send ultrasonic sound waves through one, and then it would of course have to go through the tail and then out the water column on the other side, and if there was a deflection or an effect of it, then we would know there was some kind of micro crack, and we would just kind of scan over the whole fuselage body looking for structural problems, and of course there was. Then okay, don't put that part back on the plane, then we put it back, and then the plane's certified again to fly another whatever many hours before it's got to be tested for cracks. And so using sound waves. So anyways, all of that was to say, and all this beginning part is to say, what are sound waves? They can be in solids, they can be in liquids, they can be in gases, they can be any of these molecules. All it is vibrating waves here, or vibrating molecules, one hitting another. What frequency would these waves vibrate? And the answer I'm looking for is any. I mean, this at a very low rate, I would still call a sound wave. I would just call it a sound wave with a low frequency. On the other hand, I could be hitting these molecules at a fast rate, but I would still call it a sound wave. And that's why I got a couple of these out here. You already heard this one. Here's a piece of metal. It's made out of aluminum. It's kind of thick, kind of short. You strike it, makes sound, right? If I grab a different one and compare it, you will probably notice that it has a longer arm. It is thinner. Well, going back to our mechanics, what you might think if I were to hit this one? Yeah, wouldn't it still vibrate? Faster? And I guess I want to be careful with that word faster or slower, because I'm not talking about the speed of these waves. So the rate of vibration, right? The frequency. Would this be higher or lower? Oh, I got a mix to you, right? Well, my first thought is this is longer. And so what did we learn about moments of inertia and vibrations? Right, harder to rotate this one. So I would expect this one to be at a lower frequency because it's longer. I'd also expect it to be at a lower frequency because I think it's less stiff. See, it's thinner than this one. So for both those reasons, I think this one should vibrate like that one, but not quite at the same rate. So I'll give it a try here. And of course, what I want you to notice, if you haven't already, is your ears can pick up that rate, right? This one has been measured. It's been labeled as it will vibrate 1,024 times every second. But this one's been measured at 512, half of that. So it does vibrate. Both of these do produce sound, but they do produce it at a different frequency. And so as you said, yes, any frequency from 0 on up, if I make a little scale, to infinity, would be considered sound waves. But your ears can detect that. I'll put a little mark here. The first one that I did for you was a 1,024. The next one was a 512. Yeah.
How come the rate at which it vibrates is completely independent of how much energy you put into it? Like you hit it softly or hit it really hard, why is it no different?
Well, the energy, I guess the answer to that is also, let me go back 2 chapters. Remember the spring? The spring and the mass? Right? The rate at which it vibrate had to do with the spring constant and the mass, not how hard I hit it. So if I walk up to a spring and I hit it just a little bit, it gives it just a little amplitude, but it goes back at some rate. If I hit it real hard, well then it goes really big amplitude, right? But the rate is still the same. So in that sense, it's exactly the same. And I guess the answer to your question is, giving it more speed, all I do is give it more amplitude. And it travels a greater distance. It travels faster, yes, but travels a greater distance. And so the period is still the same. Yeah. Yeah.
Is there any frequency relationship between notes?
Oh, yes. 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 And he asked if there's any frequency relationship. So this is an octave. When you get into music, some of you, if you're into music, it's not really listed here, but the mathematics or the science of the music is quite interesting. I mean, what sounds well to the human ear is usually integer multiples. So if you play a major chord like C or E, those 3 notes and those chords are integer multiples in frequency. Yeah. In fact, you're getting a little bit ahead of, I should probably say this, and I think you're getting the point before I can really answer that better, is what I want you to notice is then there are many different frequencies. Your ears pick up those frequencies and registers it in your brain, and you call that, yeah, it's pitch or it's tone, whatever word you want to put there here. But I wanted you to see the general principle about waves, frequency, that we learned in the last chapter, when applied to sound waves is your pitch or your tone. And so what I have played for you is a factor of 2 deliberately, because this would be an octave. This would be high C on a keyboard, and then this would be the next C above high C.
Would the speed of light put an upper limit on the maximum frequency?
Sure. Okay. So I'll put a stop there. So maybe not infinite number of frequencies, because but that's an interesting theoretical debate. It's not going to be relevant for this, but we're not going to get close to the speed of light. But it's an interesting one, because I could also have smaller distances. So I'm not sure there would still be a limit. There'd be a shorter distance together with that Okay, I better stay away from that one too right now. But I'm not sure it'll be quantized at that level, because to be quantized, you have to be in a box. You have to, if there's no endpoints to it, then we're not in a quantum realm. So I'm not sure we would have a quantum picture. All right, well, I'm going to leave that one alone here for just a minute here. All right, so forgetting that here, what I do want you to see, though, and I think you are getting it here, that there is a whole range of, maybe not infinite, but from 0 up to a huge range of frequencies. All of those are considered sound waves. I have had you listen to 2 of them, and so far then you've got this idea that the frequency is connected to the pitch and the tone. And I was going to wane a little bit, but since you asked that question about why hitting it just lightly compared to hitting it hard gives me the same frequency, and I think you can hear that there, okay, that is the same frequency. But what did you notice between hitting it soft and hard? Yeah, didn't it get louder? And then physically, as you said, this would be the amplitude. This would be how much is this piece of metal moving. So the general property from last chapter is amplitude. When amplitude is applied to sound waves, what do I get? Yeah, this is the volume of it. Or what we will calculate here, the intensity of the sound. How loud is the sound? And that's the beginning part of this chapter. Again, going back and understanding frequency and amplitude from the last chapter, applying to sound waves, they give us our tone, or they give us our volume of it.
Do we look at phase shift at all with sound waves?
Do we look at it? Let me answer that in 2 parts. Can your ears detect it? No. I mean, it's going back and forth. This one is 512 times a second. And so where I start, if I start now, or now, or now, the phase, your ears don't pick up the phase.
How did it go high pitched when you
Well, all right.
Sorry.
Next chapter. But besides vibrating like this, it could vibrate. Okay, so I'd like for it to vibrate just like this. I'll make a Y out of it. But sometimes it will do this on me. And and so I'll get a slightly different vibration than it's really designed to. So that's what you just heard. And that's what next chapter is about here. So a little more complications in the vibration. So here, I'm just trying to get to, like I said, some sound waves here. So I will put, and you noticed in this chart, that sound waves are all these frequencies. I focused on 2. In a minute we'll go through the whole range, but what you'll discover here is somewhere at about 20 hertz, it becomes very difficult for humans to hear it. And of course it's different for every human, but somewhere around 60 to 20, your ears are just not designed to pick up those vibrations anymore. And so we like to say then that humans really don't hear well below this number. Although that's not to say you can't feel it with your body, and these subwoofers in the theaters are all for, and in your home theater systems, they pick up those lower ones. But for your ears, you don't really pick up those lower frequencies. So we're going to put a range here. And of course, everybody range is a little different, so I don't want you to take this too literally. But we like to say humans can hear in this range. And I already heard somebody say it, that there is a range that humans pick up. And so obviously, the first ones I showed you were in that range, so you could hear it. But I just want to emphasize, if you, as a human, couldn't hear it, if it was above this frequency, is it still sound wave? Yeah. And so that's what we're studying. We're studying all sound waves, whether they be in the range humans can hear or not. They could be above, they could be below, they could be in air, they could be in water, they could be in solid, liquid, or gas. It doesn't matter which one they're in. Humans can hear it. Now, we like to classify them, and so maybe you've heard of the sonic range. That's what's called the sonic range. If a human can hear it, well, it's the sonic range. But that's not to say waves do not exist at lower and higher frequencies. So I will go to lower frequencies, or at least I'll put it on the chart here in a second before we actually try it. Yeah.
Is it a coincidence that those two things are powers of 2?
Oh. Not that I know of. No. Not.
Those are C notes, you said?
These are. Were you saying about these or these?
No, the 5, 12, and the 10.
Oh yeah, I picked them as power of 2 because that's an octave. And nothing special about that either, but just...
So C notes are all powers of 2 then?
No. Okay, so if I go a little lower, well, if I go lower than this, go to the next C, it's 256. In between that is an A at 440. If I double A, I will go up an octave to the next A at 880. So, the factor of 2 is an octave, whether it's A to A, or C to C, or E to E, or E sharp. E sharp, is there an E sharp? No, F sharp to F sharp. Yeah, B flat. Okay. So, there is the, and like I said, and I don't know them all by heart here, but the music majors are, I think they've dropped it here, but there used to be a class that the music majors would come over here. We had a retired teacher who used to teach the physics of music and get into the chords and every note. So you asked it and you sound to be interested. If I start at one note like A, 440. Okay, so here's A, and if I go up to the next note, including half steps, so A sharp, that would be 440 times the 12th root of 2. And so then if I go from A to B, that's 440, and now I'm going to go 2 steps. So that would be 2 12th roots of 2. And if I go all the way up to the next A, which is 12 steps, counting half steps, 12 notes, I would get to 440 times the 12th times the 12th root of 2, which is 2. And so every half note on a keyboard is the square root of 12 over 2. Right. But all that said, erase it. No, that's not what this class is about here. But that's why there's a nice mathematical relationship when I play the chord and I play a C, E, and F. And there'll be integer multiples of each other. And they'll sound good to me. When I play a C and a D together, there's not a nice integer multiple of those frequencies, and the blending of them sounds terrible, and and so those notes don't sound good together. So there is a nice mathematical connection between all those. Anyway, I wanted you to get a chance to hear all these, so this is the sonic, but let's put some more names here. What about frequencies that are greater than sonic? Ultrasonic. Do not say supersonic. Right? And again, goes back to waves in general. There's the speed of the wave, and then there's the frequency of the wave. Right? And I'm talking about the frequency of the wave. We reserve the word supersonic for things that travel faster than the speed of sound. These are all waves. They all travel the speed of sound. None of these waves are going faster than sound. They are not supersonic. They do not travel slower than sound. They are not subsonic. So those words are coming up here. But their frequencies have a big range. They can be higher frequencies than what the human ear can hear, so they're ultrasonic. You ever heard of ultraviolet? I think, yeah. What's ultraviolet? and I know we haven't done the optics, but it's coming up soon, right? Those would be frequencies that are higher than violet light, which violet light happens to be the highest frequency human eyes can detect. So we have ultraviolet. So going the other direction here, we have frequencies lower than the human ear can hear. What are those called? Infrasonic. And so we have infrasonic, frequencies lower than. There's not much of it, but it is. Ever heard of infrared? Sure. And what does that mean? Frequencies lower than red. And red happens to be the frequency of light, the lowest frequency of light that human eyes can detect here. So it's the same play on words, the infra and the ultra. I thought it would be worthwhile then to get maybe away from these tuning forks here and come over maybe to a little more modern way of producing sound, and you're probably more familiar with the speaker. This one doesn't work. It was torn apart deliberately to show you that inside this speaker there is a magnet. Around the paper diaphragm is a coiled wire. For those of you who had 122, you better already know this. Those of you who haven't, I will tell you. But when I pass electricity through a coil wire, it becomes a magnet. It becomes an electromagnet. So when I pass electricity through here, that's a magnet. That's a magnet. What happens when you have two magnets near each other? Yeah, they either push or repel depending on how they are aligned. And so as I put electricity through here, maybe one direction, that would take the paper diaphragm and push it out. Pass the electricity the other way, and that will pull it in. And so by alternating the current that goes through here, the paper diaphragm will go back and forth. And so this is how the sound is produced. Not very exciting, I suppose, but am I producing sound? Yeah. What range? Somewhere in that infrasonic. This is a lot less than 20 times a second, right? And so there are the sound waves, not detectable by your ears. So if I go to a speaker that has not been completely destroyed, and I say completely because partly I did, I tore a hole in the center so that convince you there is a magnet in this one too, all right? But other than tearing that little hole there, I have grabbed a little electronic box. I have turned on the current. You can see the wires connected. And again, those of you at 122, you've seen this box, but this box makes electricity go out and in, or yeah, out and in, out and in, out and in. How many times? Well, whatever the dial set at. So this is, looks like right, it's 5 and jumping down to a 4, so you know it's probably like 4.8 or something. And so it's going back and forth 4.8 times a second. I don't know, can you see it at your distance? Can you see it? It looks to me more like it's breathing. But I would ask again, is this producing sound? Yeah. Now, in the infrasonic, so it's not that you're going to hear it, but there are sound waves. There is that pattern that we were talking about going out in this room. Okay? If I turn up the dial a little bit, you will hopefully see it go back and forth a little bit faster. And also, since I tore the paper tends to flap at a frequency higher than the 13. And so if you hear something, that's probably what you're hearing. You're hearing the paper vibrating because I tore it there. But the 13, I think, is a little bit easier to see. And again, it's a low frequency that probably can't hear it. In fact, this setting of the dial, I think, goes up to 22 times a second and then stops. So right about here, I'm just getting into the sonic range here. Okay? And to show you more, I'll have to change settings. And so now, there is a combination of the loose paper flapping, but also a very low pitch and a low tone. And I think you guys in the front could probably hear it. Again, we're barely in the range where humans detect, so you guys over there probably aren't hearing it quite yet, although you're young and healthy and your ears are probably good. So maybe you do hear the 33. But as I go through the dial, I thought it would be just worth kind of wild to kind of get up here. I like the 60 range. Pretty much about 60, 70, everybody in the room can kind of just begin to hear it. Even those of you in the back, can you hear it? Okay, and it's a very low tone, right? Remember, frequency has to do with the pitch or the tone. And as I turn the dial, this one goes up to about 200 before it maxes out and I'll have to change. But higher and higher and higher and higher and higher and higher, right? And so I'm at the end of this scale. But now it's going back and forth 215 times every second. And of course, to go that many times every second, it barely moves. And so you probably don't even see it anymore. That's why I started on a low one there. I'll turn the dial down, go to the next setting. Oh, maybe I should start a little lower. So there's about the 200s. So starting down in the 200s, 200s, 300s, 400s, 500s, 600s, 700s, 800s, thousands. Right? And so now we're really right where the human ear hears really well. I mean, if you can't hear this, you need to see a doctor, because this is annoying. And I'll pause because next lab we are going to measure the speed of sound. We'll use that tone. Everybody in class for 20 minutes will be broadcasting this tone. So you might want to pack some Advil or aspirin or Tylenol there, okay? All right, so there's our 1500. Well, I'll keep going just to kind of go through this. Maybe we'll go a little quick since A, we need time, and B, it's annoying. But there's 2000. Turn the dial back down. Go to a higher setting. There's 2,000, 3,000, 4,000, 5,000, 6,000, 7, 8, oh that's annoying, 9, 10, some of my favorite, the 13.5. Real high frequency, annoying. It's my son's ringtone. You know why they put out those ringtones? Yeah. They say that that's the frequency range you start to lose as you get older, so old people can't hear it. So my son thought it would be fun to put that on his ringtone, and he wouldn't have to worry about turning off his phone in class. And nonetheless, it went off in class, and he doesn't think his teacher heard it. He goes, oh, I don't think she heard it, but everybody in class screamed bloody murder and knew his phone was on, and he still lost his phone anyways. But nonetheless, there's the ringtone. Keep going. 16, 17. And it's and now we're at a combination of my age, and this speaker is not really designed for those higher frequencies, so it doesn't play it real well. But there's 20, 21, 22. Yeah.
The part that you described was for producing those high pitches.
Oh yeah, I did, didn't I? Yeah. All the more reason it doesn't work there, right? All right. So, anyways, we went through there, and like I said, just to give you a kind of a rough idea of this idea of the sound waves. Now, with all that in mind, let's see. We've covered frequency. I think at this point, and that's what I kind of wanted to do in this first half hour, you got a good idea of what waves are, right? Or at least what sound waves are. And so now I could ask things more in depth, like, well, what is their speed? And why does it have that speed? Could its speed be changed? All right, well, maybe I'll just start there. What is the speed of sound? V equals. Oh, speed of sound. Well, before I answer it in too much detail, how about if we go back a chapter to a string? Now again, last Tuesday I didn't work this out. I hope you did take the time to kind of look at it. But I took the time to examine that equation a little bit better. I took the time to say, well, what is the speed of a string dependent on two factors? And you did a lab on it this week. Oh, well, I guess a third of you still have to do it this afternoon, but 2/3 of you have already done this. And the whole point was to say that there should be two important factors that determine the rate at which these waves travel. The T was the tension, right? How tight is the string? And I was kind of describing it to you by saying, I hope that makes sense, because that is the part that pulls the string back. If I lift it up and let it go, it's the tension that is snapping it back. So more tension means, of course, it's going to go back faster, right? This is kind of like Newton's second law. And also, more mass means more resistance to go back. And so we have mass on the bottom, we have a inertia effect, and that's what I want to put here. All of our waves really involve a combination of some kind of inertial property and some kind of elastic property. Something that is pulling the material back to its original place, and something that resists it from going back. Usually it's mass, it's an inertia property. And that's the string. We didn't give you an equation for the rods, but those rods that I had out here, remember we had the short rods and the long rods. Wasn't it the short ones that had a higher speed? And we argued there that they did because they had less inertia, in this case rotational inertia, moment of inertia, where they would want to take a bigger effort, or the smaller ones could go back easier than the longer ones. Well, the same thing can be said about sound. Sound would have both an inertial property, and I'll start there. That one kind of makes the most sense. Notice I did not derive this equation, nor does your author derive it quite yet. He waits till a couple of chapters when we get into thermodynamics, and he, like I, are just going to take the easy way out and say, look, this might be a little too much to discuss yet, and in our case it's factor of time and factor of we haven't got into our thermodynamics, but he says, take a look at this, and I guess I meant to call up the diagram here in 7th edition. What chapter are we in? 17. But that's, I wonder why the icons aren't shown, but nonetheless I found what I want. Here's this table, and in this table, as you do the homework, you're going to be given sound waves. Some of them will be in solid, some of them will be in liquid, some of them will be in gas. Let's look at the gas here. Look at, we've got hydrogen, helium, and air, right? Air is more dense than helium. Helium is more dense than hydrogen. What do you know just about their speed right away? Yeah, right? Their speed is related to their density, right? And so the lightest density of the materials here, the hydrogen, has a higher speed. It doesn't take much to get hydrogen to move back. So that kind of makes sense. So this one you're familiar with. Now this you may not have seen before. This is referred to as a bulk modulus. Those of you who have done our Engineering 115 may have seen this. I don't want to spend too much time other than what is the bulk modulus. It is just a way to measure if I squeeze something, how much does it push back? Oh, we like to label it this way. We call it B, but we say, how does the pressure change when you change its volume? That's really what that is, and we're going to see that as we get into thermodynamics here. But so far, we're not going to mess with it. In fact, some of you have already done what we call the ideal gas law in chemistry. PV equals nRT. Isn't there a connection between pressure and volume? Right, and so when you take a gas, or for that matter, a liquid or a solid, if you take it and you squeeze it, you put pressure on it, how much does its volume change? If its volume changes a lot, that means it's pretty easy to squeeze, right? That means it has a small bulk modulus. That means the speed of those waves would be pretty small, because as you squeeze them, they're like, I'll come back, I guess. If I must. They're just kind of lax about it. But if it takes a lot of pressure to squeeze it, then what you're saying, when you let go of it, it's going to snap back really, really quick. And so, again, without explaining too much about bulk modulus, you will see then the general principle that whether we're talking about waves on a string, whether we're talking about sound waves, or whether we're talking about those rods I have, the speed of the wave is a combination of the elasticity of the material, how easy or hard does it compress, versus how much density does it have. You would expect, wouldn't you, solids to be harder to compress than gases? They're also more dense too, so maybe it's not so obvious, but I would think that the speed of sound in the solids because of that would be much higher than the speed of sounds in the gases. No? And let's see what we have. Here are the gases. Here are the solids. Here's a real nice, stiff solid, right? There's the speed of my aluminum. Nice, solid piece of material, snaps back really well, and relatively light. Huge speed, yeah.
Why do they have Pyrex glass listed?
Why do they have Pyrex glass?
That's a proprietary formula that changed a couple decades ago.
Well, and aren't there different types of Pyrex? No? I know there's thousands of different types of glass, like BK7 we used to work with.
Yeah.
So, you're saying they should be more specific. What type of Pyrex? Yeah, okay. I don't know. Probably mostly because that's what we use in the lab, because Pyrex can handle the heat and we don't usually use any other glass in the lab other than Pyrex. That would be my guess. But anyways, I did want to make sure you saw that general property here, that this would be the speed. So, as I said, without proof, there's one equation, here it is, I want you to see today, that is derived without proof. As I said, it's coming up here in when we do our thermodynamics. But you can imagine then that this bulk modulus, as well as the density, has some relationship to the temperature, or maybe you don't know that yet. I know you saw it in 102. What's the difference between something hot and something cold? Right, how fast those molecules are moving. So, I'm hoping you will see here that this bulk modulus, as well as its density, must be connected to its temperature. And so, I would expect for sound, the speed to depend on its temperature. That's really what I'm trying to get here. And that's all we want to really get at. Like I said, getting this formula with the bulk modulus, the density, why it's a square root, that's more of a thermodynamics question coming up in a couple of weeks. The fact that it is worked out to be related to the temperature is, again, something we'll come up with in a couple of weeks. But it does illustrate it well in this table. There's air twice. One at a lower temperature than the other. What do you notice? The speed has changed a little bit, right? The speed does depend on temperature. So it depends on the material, and it depends upon the temperature. I would suggest this, since we use it so much. We talk about the speed of sound in air near 20 degrees so often. Commit the 343 to memory, okay? All the other ones we can look up or calculate. I wouldn't expect you to know those, but I would expect you to know, and your author does, if you are talking about sound waves in a lab, it's usually near 20 degrees. It's not near 0 degrees, and it's not near 100 degrees Celsius. It's near 20 degrees. And so that 343 is going to be a number that you're expected to know as you do the homework.
In your calculations, is humidity just as important as temperature?
No. Humidity does matter, but not nearly as much. No, not, yeah. So, I'm going to give you two equations here. The first one your author gives you is after you do this math, it comes out to be 331 times the square root of 1 plus the temperature on the Celsius scale divided by 273. And like I said, I just hate to do that, but it's important that we move on. That's the equation results, and that's what your author wants you to see and use. In fact, he even goes one step further here. K for Kelvin, PK? Temperature, C. C?
I thought you said Kelvin.
Oh, did I say Kelvin? No, Celsius. Actually, for those of you who like Kelvin, it's better to see it on the Kelvin scale. At least the equation's a little bit easier. It also kind of makes sense because the movement of the molecules is related to the temperature on the Kelvin scale, and so the formula and the relationship's a little bit easier. So, again, I digress here, but that would be it on the Kelvin scale. And it makes sense because it has to do with the motion of the molecules. So the speed has to do with the motion of the molecules directly, and that's what the Kelvin scale is. Yeah.
Is this specifically for air or something?
Oh, and yes, and I should emphasize, this is specifically in air. Yes, good point. This would not be the speed in aluminum up there or in water. This is in the air, yeah.
So the only thing that would change is the 331, the coefficient, right?
No, because you can have some intermolecular forces. But I'll say for mostly, yeah. Yeah. When your molecules get, yeah. Yeah. See, but this would still be true in my solids. But the compressibility of it would depend not just on the motion of those molecules, but the intermolecular forces of those. So the waters and the liquids and the solids do get a much more complicated formulas. And of course, at this point, we won't be doing any of that at this level. That'll be your next level if you go on to that. But there's a nice equation. In fact, your author does one more thing. He says, hey, remember that good old Taylor series? Remember from your math class that a Taylor series meant that you could take any function and write it as a polynomial? And that polynomial would look, I guess, something like this. It would be an infinite sum of n going from 0 to infinity. Here's the polynomial. You have to pick some value of a, any value you want, as long as the function is continuous at that point. You would then take the nth derivative of the function evaluated at the point a. And so this would be an infinite sum. And so if you had a function that was really complex or maybe hard to integrate, you could change it to a polynomial. And aren't polynomials really easy to integrate? Right? And so I was going to kind of brush over this, and I got to thinking about it this morning. I said, that's worth saying right there. Because I could already tell when I said Taylor series, I heard a lot of moans. No, not a Taylor series. And I know when you're exposed to them in a math class, they can get really hard and kind of miss the point here. And I'm not even going to really do a Taylor series other than give you the result of it, or I'll even look it up in Appendix B there, and what is the result of this. But I do want to say this. It is a very, very powerful tool for the scientist and the engineer, because so often in the real world, the real equation is very complex. And when you go to try to do an integral of that, it can't be done. So we can approximate it. So we have something to work with, right? And polynomials are so easy to work with. Or I shouldn't say so easy, but a lot easier to work with. And they're really easy to integrate or differentiate, right? And so changing a function into a polynomial is kind of nice. And so this function, 1 plus x raised to a power of n, if we did take the time to do this, setting a equaling 0, a equals 0 is a nice one because x minus 0 is a lot better to work with than x minus 5, and then you raise it to a power of 10, right? But what you can see here is you would start to get a pattern so forth and so on. And I'm only saying it now, like I said, not so much to do the Taylor series, because that's not really the point here today. But the point here today is to say, I could take something more complex like this, which this isn't too bad, it's a square root. But you are asked to put that in the denominator and then integrate it. And so I'd say, stay away from putting it in the bottom and integrating the square root. Change it to a polynomial. Because here's really nice. What if x is small? Look closely at this. If x is much less than 1, what do you begin to notice? Even though technically this is an infinite polynomial. Yeah. If x is, say, a tenth. I pick on a tenth because room temperature is about 20 degrees. Fair enough? And so this is 20 degrees up to maybe 30 degrees divided by 273. Isn't that about a tenth? Somewhere in the neighborhood of a tenth? So if I have a tenth here, and then I go a tenth squared, what do I get? Hundredth. It's pretty small, huh? How about cube? A thousandth. All these are small enough to ignore. And so something that looked like it might be a little bit harder to either integrate or differentiate or whatever the math function I want to do, put into a program, I can change real simply. In this case, I can write approximately 1 plus n. And so if we do that to this equation for the velocity of sound, we come up with this. The velocity of sound as a function of time will be the 331 and actually closer to a half. I didn't put the half on here. Plus 0.607 multiplied by the temperature in the Celsius range. And so this means that the velocity does change on temperature, and it changes in kind of an easy way as long as you're really only going to go 20, 30, 40 degrees. You start to get to 200 degrees. This step of erasing the higher part of the polynomials isn't valid anymore. So that's why I guess I should really write this as approximately that. And so feel free to use that equation again and again and again, and that's what your author will do. You'll see that.
So it says that error is 331 right there. If you plugged in 0 into that equation, you would get 331.5.
Yeah. Wouldn't I?
Yeah.
Are you asking? Yeah, right.
Well, wouldn't it, doesn't it say it from like, it says that 0 degrees Celsius would be 331?
Is it?
You get 1 plus 0, which is just 1. Square root of 1 is 1.
Right.
You get 331.5. Wouldn't it just be, I mean, is that
Oh yeah, okay, yeah, they're rounded. Yeah, yeah, they did not include the next significant figure. And I hope I'm remembering it is a 5. But to answer your thing is they have rounded. I mean, there's something else. It's 331 point and a 4 or a 5. So they just rounded there. Yeah. But good. I'm glad you see it though. You can see that if you put in 0 there, or if you put in 0 there, you see that the speed of sound is 331. So 331 is roughly the speed of sound at 0 degrees. And so when you get to 20 degrees, you get your 343. Yeah.
Is the original equation valid for all temperatures, or is there places where that actually breaks down?
It is valid so long as the bulk modulus is valid. And they derive this, again, like I said, when we get to our thermodynamics, which with the ideal gas law. So it is valid on a pretty good range until you start to get to a phase transition. So if you start to get to the point where the gas is cooling itself, it wouldn't be, I mean, it's turning into a liquid, you know, which I guess if this is air, which is mostly nitrogen, and if I remember, nitrogen turns into a liquid at about 80 Kelvin, if I'm remembering right. So as long as I'm far from 80 Kelvin, it's pretty accurate. Yeah.
I'd like to continue on my question. Looking at the equation, 331 is kind of multiple for it, so we're multiplying inside of the root. And if that's at 0 degrees Celsius, how would it's below 0 degrees Celsius? You can't decrease to 31 to the negative number because the root is above.
Yeah, if I was less than 0 degrees.
Terrible math in my head.
Okay. So you answered your own question. Good. Good. Yeah. All right. All right. Well, again, maybe I spent too much time here, and like I said, I debated this morning, but I thought, you know what? Even though this chapter's on sound, it's worth just going through and mentioning Taylor series. That's what I was after. Really wanted you to see that clue, because like I said, it's easy to go through the map and say, yeah, I won't need this. You will. You will be using Taylor series. I know we haven't really used it quite yet. This is kind of the only time we've kind of touched on it. We'll touch on it again. But when you transfer from here, you will see the Taylor series again and again and again. They're just a nice way of taking something that is more complex and simplifying it. Well, I'll keep going here. So that was, one of the math questions about what is the speed. All right. How about the equation for this wave? I mean, maybe we should draw the picture here again. If I were to take this tuning fork and I were to strike it again, as we talked about, as it swings over, it would compress them. That would move, let's do a quarter, maybe about here. And maybe I'll put a little dot here and a dot here and a dot here. And look at this a little bit closer. Let's kind of look at in between. You see, the description I gave you about a half hour ago was only to looking here where it is compressed. That is, I took the metal piece and I knocked it forward, right? And so this went and was compressed because these molecules over here were shoved over to here. Fair enough? And of course that migrated onto here. But what about halfway in between right here? What was happening here? What happened to this metal piece? When that metal piece was shoving the molecules this way, what did it do next? Yeah, it shoved the molecules back the other way. I mean, at first it shoved them this way. And before it shoved them that way again, halfway in between, wasn't it pushing the molecules the other direction? Weren't these molecules here being shoved away? Right? And so what I have is a series of areas that have slightly higher pressure because the molecules are concentrated there. And then I have areas of slightly missing molecules because they were shoved away, right? Now I say all that because that really gives us two ways to describe a wave here. Maybe I better put a title over here and say, look, what would be the equation of these sound waves? We did the equation for waves in the last chapter. So this isn't supposed to be a hard exercise, but it is this question. Do you want to describe the wave by the displacement of the molecules? What you might call the amplitude. How far did the molecules move? Or do you want to describe the wave by what is the pressures it has created because of the movement of the molecules? You see what I'm getting at? And so what I'm trying to say here is we have to make a decision. And what we'll do is we'll do both. And we'll wait till whatever is important to us. Do we want to think of this as a displacement wave? Do we want to think of this as the molecules have been moved from one place? Or do we want to think of them as the pressure at that point? Because the molecules are at that point. Here's why it matters. I mean, let's go through this. I left right below it open because if I put a straight line down here and call this my x-axis, and I draw a line down here and here and here and I look at the movement of the molecules, I would say that at this point, and here's where it gets a little tricky here, the molecules that were at this point, and I say we're at this point, are they there anymore? No, they got pushed, right? Their home location is here. And now they got shoved to there. Now they're going to come back to here and get shoved to here. Okay? But their home location is here. So I am going to put at their home location, their displacement is up here. Here's what gets kind of confusing. I'm going to say, even though they've moved on the x-axis, I'm not going to plot them on the x-axis. Fair enough? This is the difficulty of longitudinal waves. Understanding a graph of longitudinal waves, I am going to plot how far they moved on the x-axis, but I plot it on the y-axis. That makes sense? In fact, your author does this. He goes, maybe it will be less confusing if we call that S and just get away from the notation of x. Please remember, though, the molecules move in the x direction. But so that I can talk about the x position of the wave separately from the x position of its vibration, I will plot the vibrations this way. Fair enough? And so as I plot them this way, do not think they are transverse waves. That's really my warning. We will draw pictures that look like transverse waves. That's not what we're trying to say. What I am trying to say is the molecules at this location, their home base, have been pushed forward, and that's why I will put a mark there. These molecules, their home location was right there. They didn't get pushed anywhere. What happened is these guys over here joined me. And so that's kind of what the plot would look like. These guys moved over to here. These guys moved over to here. These guys moved over to here. These guys here didn't move as far to get here. These guys here moved a long way to get here. Fair enough? Now, let's look closely then at, remember why this was a vacuum? Right? Let's see, did I mess up here? Yeah. Wait. That this over here then was the reverse effect when the rod was coming back. And so it's these guys here that are no longer here. They got shoved over to here, which is kind of why these are beginning to spread out and a vacuum is beginning to get created there. Then the whole process begins to repeat itself. These guys got shoved over to there. So simply put, these guys are going that way, negative. These guys are going this way, positive. These guys are going that way. And we can kind of draw. And unfortunately, I didn't do a good job with equally spacing them there. But what I am trying to say then is if I wanted to mathematically describe this wave, I would be saying cosine of kx minus or plus omega t, some maximum displacement is the displacement of those waves. Fair enough? On the other hand, we could describe this wave not in the position of the molecules, but more of the concentration of the molecules. We could describe this as a pressure wave. So when we do that, I'll change to green here, you can hopefully see right here we have a lot of pressure. We have a lot of pressure because these molecules were sent that way. That's what the up part means, go that way. And right here, this is saying send the molecules that way. And so we've got a large concentration of molecules there. So we have a large pressure there. And the molecules are missing here as we send them that way. This kind of elongates here, and there's a lack of molecules there. And the part that can get confusing, hopefully, is twofold here. Is number one, are you plotting the displacement of the molecules, or are you plotting the pressure of those molecules? Do you see how the equation would be different? Wouldn't this be a sine kx minus plus omega t times some maximum, and I'll call it maximum change in pressure, because the atmosphere already has a pressure. So there would be, as those little clumps go to your ears, there would be a little higher, a little lower, a little higher, a little lower, a little higher, a little lower. And so, as you will read, or hopefully have even read here in this section, your author takes some time to mention, hey, as we describe mathematically these waves, and as we look at the effect of these waves, we can say, are they displacement waves or are they pressure waves? Both are valid, but they are 90 degrees out of phase with each other. And so we got to be careful on what we're talking about and why we want to know something about those waves here. So that's why I kind of tried to work all that out, but you know, in that picture there, and say, okay, we can look at it either way. And of course, the second thing I already mentioned, but I'll say it again, be careful when I draw a plot this way, and I write an equation this way. I in no way mean that the molecules move up and down, right? The up and down on the graph is the movement left and right that the molecules move. The x on the x-axis is the home base of those molecules as they move back and forth. They oscillate around an average at home base.
And the pressure is good.
Yeah.
The amount of pressure that there is, like the amplitude, that wave,
Yeah.
how much pressure there is?
Yeah, so how much pressure has increased? So right now, if there was no sound waves in here, there would be a certain pressure. And then when I start talking, the air molecules would go slightly up in pressure. So there would be a increase and decrease in pressure. That's what I'm plotting. Increase and decrease in pressure when somebody has some sound waves versus no sound waves. And so that's what your ears pick up. Your ears are already at atmospheric pressure, and when somebody starts talking, that pressure goes up a little bit and pushes your eardrum in. And then it goes back and your eardrum comes out. And back and forth, and back and forth.
Could you explain to me what the X and Y for the displacement graph is again? And why means the...
So the X is probably the easiest one. It is actually the position. Here is the sound waves. X represents the position in space. I like to call it represents the home base of where this molecule is if there was no sound. And then when sound waves are created, it's no longer going to be at that X position because it's going to be moving. But nonetheless, I'm still going to plot it right here. And how much it has moved from its home base is plotted this way. Not this way. Otherwise, it's kind of hard to draw. But like I said, my warning is, I think too many students look at this picture and they see the up-down in the picture and they think these are transverse waves. And sound waves are not transverse. They're longitudinal. How much do they move? All right. Well, I'll keep going, yeah? Go on.
Why is the change in X 0 at the vacuum? Wouldn't that be when all the particles are away?
Well, okay, maybe all but one. And so I guess what the here where the pressure is low, the molecule that's at a home base here doesn't move. What I'm saying is all of these molecules go then, let's see if I got this right here. So all of these are going to get shoved in that direction, negative, right? But even these here are a little negative. These are a little negative. These are a little negative. These are a little negative. Then we cross to the other side. These are going positive. So everything over here goes that way. Everything over here goes that way. Maybe one molecule stays there and doesn't move. But that's why there's low pressure, because everything else is kind of moved away from it. Everything except for exactly that one. But everything else near it has gone away from it. And like I said, I think that's a little bit harder to see. Well, like I said, I better keep going here. Uh-oh, especially with the time here, although maybe we're doing pretty good here. We talked about power for at least waves on a string, didn't we? Well, let's continue with that discussion. The truth is we won't focus too much on power, but we will jump over to intensity. And we didn't use intensity yet, so I will introduce it. And for that matter, we didn't do sound levels yet, but let's talk about that. In fact, my warning here is sound levels and intensities often get confused. So let me start with power. What was our definition of power? Energy per time, right? That's why we measured it in watts. And when it was a string, what did we get in the last chapter for the power that was being transmitted by this string? And so visually, if I were to stand here and take this string and go up and down, didn't we come up with this? And we didn't derive it. I kind of left that for the author to do. Didn't we have a 1/2 times the mass density? How heavy is the rope? How fast is it traveling? At what rate is it vibrating? Its frequency squared and its amplitude squared. Do you remember that from Tuesday? And again, I didn't derive it. I just said, look, your author did a good job of deriving it, and I think he did. And he came up for this as the power. All right? So, working with a string, that made sense. Because as this wave would go down, the energy would be approaching the other side at a certain rate, right? How many joules every second? Let's talk about sound waves, though. As you'll begin to see, sound waves aren't quite as useful talking about their power. Because if I had a speaker right here, and let's say the speaker put out 1 watt, that's 1 joule every second, which, by the way, is a lot of sound energy. If you have a speaker that says, oh, 100 watts for every speaker, and you have 4 of them in your room, be careful. What does the 100 watts mean? Okay, that's how much electrical energy it consumes. And 99.9 of that is all going into heat. Very little is going into sound. I mean, 1 watt of sound is quite a bit. In fact, I thought it would be worthwhile to take a moment with this crazy guy. I like him. Because this guy puts out 1/2 watt. Small amount, right? No. It consumes a lot more than 1/2 watt. But at sound level, the amount of sound energy it puts out is only 1/2 watt. Small, right? It's going to consume more than that, so I better get the big battery. 1/2 watt. Do you want to hear it again? Right? And I didn't even get a chance to get to its full 1/2 watt. I'm probably only 1/4 of a watt here. Your ears are very sensitive, and I thought I was going to use this, and you're going to see this in the number. There's not much total energy in sound. It does not take much energy for you to hear it. It does not take much energy for your ears to start bleeding and you curling over in pain. I mean, there's not much energy. For those of you who go back to 121, you might remember that usually when we did the momentum, we had to have like a stationary cart and another cart of equal mass but moving. It collides, they hit, how fast are they going? Well, we did conservation of momentum and we said half the speed. We looked at the energy, kinetic energy, and said, well, we have half the kinetic energy after the collision as before. We then thought about conservation of energy. So, well, where did that energy go? Heat and I usually get, I can't remember what semester you have, but I always have people who say heat and sound. And my first response is, sound is so small, let's not even think about that. And that's true. This is an illustration of that. This may be consuming 100 watts, but it's only putting out, and this is a highly efficient speaker, less than 1/2 watt. And so that's why we ignored the sound all the times before, and you'll see that in the numbers here. So like I said, this is not really much energy. And so sound is not much energy, a simple 1/2 watt. However, what I was getting at is even one step further, is that when we talk about the power coming from this speaker, if this is a 1/2 watt, where does that energy go as time progresses? Yeah, doesn't it get spread out on a bigger and I'll just call it a sphere. This is kind of directional towards you, but let's just say the sound goes equally that way and that way and that way. Isn't all of that power being spread out on a bigger and bigger circle? And you probably already know, as you get further and further and further away, it's not going to be as loud. So we're not usually interested in how much power is coming from this speaker. We are literally more interested in the concentration that goes in our eardrum, right? We are interested in what? Power per area. And so there's our new quantity for this chapter, intensity. The intensity of the sound, what you would call the volume of the sound, is not really how much power is there, but it is how much power per area. You know, my eardrum is this big, and I'm really interested in not the total power from those speakers. I mean, my neighbors down the street are a long way away, and I really don't care how loud they play their band in the garage. What I'm more concerned about is how much energy is it on my ear when it gets to my house. Fair enough? There's a distance involved. There is, what is the intensity? That's really the volume. So unlike the string, it is not an issue of how much power is there, because all of that power goes one place, down the string. But for sound waves, because it's three-dimensional and it goes out into space, I am more interested in intensity. And so watch what happens if I take this equation and I now extend it to sound. I might start with power and the same equation that was derived for you for the power, but focus a little bit more on that term. Again, looking at a string, that was the mass per length. Question?
Can you focus sound waves like you can focus light in a laser?
Oh, you could. Yeah. And that's probably best explained in the next chapter, and even when we get into our optics. But using the super principles from last chapter, if I had sound waves where we're going in every direction, if I then took a second speaker, and maybe a third, a fourth, a fifth, a sixth, a seventh, and a whole array of speakers, such that this speaker here and this speaker here would make destructive off at an angle, but constructive that way, then instead of the sound going out equally, it would be heavily concentrated in one direction versus the other.
Doesn't the Navy have a weapon that's doing that?
And the Navy has developed these, what they call the non-lethal weapons, where it's this big array of speakers, 100 by 100 speakers, and essentially just goes straight at you. And it'll knock you out. So the sound waves are literally like a river, where you can stand out of the river and you don't get wet. And you take just one step and it'll knock you over. And so it's a well-focused beam. And that's what a laser beam is too. You do that with the light waves. You can do that with the sound waves. A little harder with sound waves because their wavelengths are bigger. But yes.
Would it matter what frequency it'd be at, or if it was really low or really high and you couldn't even hear it, that it would still have the same effect on you?
Well, yes and no. I mean, if it's just this one, it's annoying enough to bother you. Your head can't think you straight. If you are trying to drive a boat loaded with bombs towards a destroyer, and you get blasted by one of these things, you can't control the boat, and you don't then blow up the destroyer. So that's why the Navy has this one. Obviously, they built it after the U.S. coal bombing. And so that's the intent of that one. If we go back a chapter, remember the resonance. Remember things vibrate really significantly when you're just at that right frequency. So if you just want to annoy somebody and turn them around, that's one thing. But your body cavity, especially your sinus cavities and your livers, would vibrate at a certain rate. And if you tuned it into that one and had your liver vibrate, it could rip, tear apart, you could bleed to death. I mean, there could be, instead of non-lethal deterrents, there would be lethal deterrents. And they say the CIA has those, but I don't know what the CIA has. But they can focus it on somebody, and they would collapse and be bleeding from the nose because their sinus cavity ruptured, and without medical help will die real quick. Yeah. So yes, the frequency does matter in cases like that. Yeah. So jumping back here into the math, remember this is mass per length. If we kind of think of these sound waves in the simple terms of just length for a moment, you might say this would be the mass per volume times the area of where that sound wave is. And so what I'm going to do is then replace mass per length with mass per volume times area. The symbol we often use for mass per volume is rho. The symbol that we like to use for area is capital A, but I'm a little concerned about that. Why? Because we have an A for amplitude, so let me spell it out for the moment. It's going to go away here in a second anyways. But I'm going to put then this step. When I move area to the other side, I get the intensity of the sound wave. And so this is what I was after. And even kind of talking about it on Tuesday, what is then the intensity of sound? Notice I said intensity, not power. Now obviously they are connected by the area, and some of your homework problems are going to make you think about that. As the sound goes out, it would go out in a sphere. How would you calculate the area of a sphere? 4 pi r squared, right? So if we knew that, if we were told the speaker puts out a half a watt of power, and then we stand 3 meters away, then we know that that power is then spread out on a sphere, 4 pi 3 cubed. If we know the density of the air and the speed, and we're told that the frequency is 400 hertz, could we find then the amplitude of the movement of those molecules? Yeah. And so those are the kind of questions you will be asked to. But again, then the intensity depends on, kind of like the string, the intensity would depend on how much does the air weigh? How fast is the air moving? At what rate does the air go back and forth? And how far does it go back and forth? That's why I was saying earlier on, or I guess no, it was on Tuesday, I said if you just had a tweeter speaker, to get a lot of intensity or power from that speaker, you really don't need too much movement of your speaker, because the energy can be buried in the high frequency of it. But on the other hand, a subwoofer, where our frequency is really small, we need to build the speaker with a little bit different design, a little bit of different movement. And that's why we have speakers of one design that do the low frequencies, and speakers of one design that do the higher frequencies, and then even the mid-ranges in between here, because we're trying to get the certain intensity, and we want different movements to that diaphragm that moves back and forth. I thought I saw a question today. Get it? Okay. Oh, and I'll keep going. But that's the idea of intensity. My point is, we will probably focus more on intensity than we will on power. Although the power spread out over an area is the intensity. And so obviously, as we get further and further from this speaker, the intensity gets less and less, because all of that power is spread out over a bigger area.
So by area, you mean the surface area of that sound wave?
Right, right. The simplest case is not something like you were suggesting the energy be focused, but the simple case of here is a speaker and the sound goes equally in all 3 dimensions, so all that power is spread out on a sphere. Yeah. Now, let's go to this next step. What is sound level? Oh, good. It is measured in units called decibels. In fact, maybe I should backtrack up to here. What would be the units for intensity? Yeah, I didn't mention it thinking it was fairly obvious. I'm glad it is. It would be watts per square meter. How much power do you have in a given area? But this sound level is connected to intensity. And I think so much so that it's why people confuse the two. They are so close that when you are saying one, you are really saying the other. But when you say sound level, you're really saying what is the intensity compared to some reference intensity. And so it's not an absolute number in the sense that it is watts per square meter. It is a comparison. It is, well, how much louder is it today than yesterday? That's what I mean by the sound level. Now, when it comes to sound, we like to do it this way. What's the intensity compared to my reference? And my reference, I will call I naught. I just want to check, what does your author use? Ah, good, he does use an I naught. He calls this point, then, the reference intensity. And so we need to pick some kind of reference. The standard is what we call the threshold of hearing. What is the intensity that the human ear, on average, I mean obviously everybody's human ear is a little bit different and it even changes with age and with frequency, but on a rough average, what is the smallest intensity that a human ear could hear? If you were to get in a room, close all the doors, perfectly soundproof, somebody put up a speaker, turned up the dial, how much intensity would be just enough before the human said, oh, I hear it? And maybe you've even done, ever done those hearing tests where the doctor puts the ears on and you're supposed to raise your hand, I hear it, oh, no, I hear it, oh, left ear, right ear, you know. And that's what they do. They change the intensity at different frequencies. And they say, well, what's the minimum amount you can hear? Now remember I said it's pretty small. Human ears are pretty accurate or pretty sensitive. And it doesn't take much. 1/1,000,000,000 of a watt per square meter is all you need. 1/1,000,000,000 of a watt. I find that amazing. 1/1,000,000,000 of a watt in a square meter. And the amount that goes in your eardrum is a lot less than a square meter. So a lot less than 1/1,000,000,000 of a watt goes into your eardrum. In fact, maybe your eardrum is 1 square centimeters. So, you know, that would be another 4 zeros. So 10 to the minus 16 energy or power, watts, go into your ear and your ears will hear it. Less than that, you won't hear it. But that's our reference point. Yeah. Yeah, I would commit this to memory. I wouldn't hold it on you. It's kind of like when you, 121 about G, you know, it's one of these things I go, you should know this one. Speed of sound, the same thing, at room temperature. You should know it. If you forget it on a test, come up and ask it, and I'll, you know, do the standard. Really? And then I'll write it on the paper, you know, I won't take any points off for it, but yeah. Now, so this is what we mean by sound level. Now, we're not quite done, because in another amazing part of the human ear is they can just hear up to here. But they can hear all the way up to 1 watt before what we call the threshold of pain, before you start grabbing your ears and its blood starts coming from them and you say, okay, you know, no more. That's a huge range, right? I mean, that's a range of 1,000,000,000,000. So to make the scale smaller, as many of you probably are well aware of, what's the next step we do? Yeah, so we write sound level, and we do this with a lot of quantities, like this. I'm not quite done, but we write it as the log of the ratio. So I'll say it again. Sound level is really not intensity. Now, is it related to intensity? Absolutely, right? The sound level is what is the intensity compared to the threshold of hearing. And more than that, it's then the log of that. And if you look at the numbers we are dealing with, if you were just barely hearing it, these two numbers would be the same, right? And so that ratio would be 1. And what is the log of 1? Log of 1 is 0, right? So a sound level of 0 means that's where you first start to hear it. Okay? If it was less than 1, the log of something less than 1 would be negative. So a negative sound level means it's too small. A human ear can't hear it. But at 0, you can just begin to hear it. In fact, how big would it get by this? Well, until pain starts coming in, this would be 1 trillion times bigger than that one, right? So what's the log of 1 trillion? 12, right? 10 to the 12th, take the log, you get 12. Okay, so this scale would go from 0, barely hearing it, to 12. To make it a little bit bigger, we'll put a factor of 10 out in front. The symbol we like to use for sound level is the symbol beta, and that's what I'm getting at. So there is our equation for sound level.
So both modules and sound level are related?
Oh, no, they're not related. Same symbol. Yeah. He was asking, by the way, about that bulk modulus at the beginning with the beta. No, we'll never see that this semester again. We'll see that in our Engineering 115 in the fall. But we use the same symbol, but they're not connected. This is our symbol. Yeah.
So I know like speaker efficiency is rated in terms of decibels, so they're using the same definition.
Well, yeah, it's okay. And so we can use this same definition to measure mini comparison of waves. This is a comparison of what am I hearing now? What is the intensity compared to the lowest I hear? I think what you're referring to is what might be called the signal to noise ratio, where you're saying, okay, if I send a signal in there, okay, what actually goes in and what gets played is not quite the same thing. Okay, so what I would want to know is how much do I hear compared to what has been added to the sound because of the speaker. So there's my reference, my noise. It's signal to noise. And that too can be labeled as a log, and often is. Electronics do the same thing. I know my home entertainment center has a decibel scale on it. And maybe I should use that moment. What are the units then? Yeah. They're in dB. So anytime you see this dB, what it means is they're measuring things in decibels. And what they mean is they are measuring something compared to a reference on a log scale. And unfortunately, on my home entertainment center, and they do this a lot in electronics, the reference is full volume. Okay, so if I am playing it at full volume, what's my reading? 0. But if I'm less than full volume, this ratio is less than 1. What's the log of less than 1? Negative. So everything on mine says negative. Full volume it says 0, and then as I turn it down it goes -2, -4, -8, -16, -32, and so my volume is based on a decibel scale, but it's all negative values, which I don't really like, but there's got to be a reason for it.
So you're saying the max sound level is 12, right?
Well, then that's times 10, and you mean?
Oh, okay.
So yeah, I would go log of this ratio. And that'd give me a 12, multiplied by 10. And so the threshold of pain, you said the loudest, but that's not the loudest. The threshold of pain would be 120 decibels. But I can have sounds louder than 120. It just would be also above. In fact, your author, I think, does a good job of listing a bunch of sounds there. And he even shows a little chart, and he goes, yeah, there it is. And he says, look, all the way up to, and he's got things like a whisper, a conversation, birds, a shout, a motorcycle, a car horn, and all of those are below 120. Then he gets to that 120, now he's at rock concert. Above that, he gets to jet engines. Above that, he gets to large rocket engine. So I mean, you can be above 120 decibels. It's just you know, and obviously that's how close you are too. Underwater sonar communication, an important one around here because our Navy's always testing out at the Channel Islands, and then they're always in conflict with the environmentalists who are worried about the wet migration of the whales and the communication of the whales, because those can be some high decibel if you're close, and so they'll, you know. I mean, it costs the Navy millions of dollars to set up an experiment only to stop because they got to wait 3 days for the gray whales to go by and then run the test. Yeah.
The sound level equals B. Is that beta? Is that both modules or completely different?
Completely different. Same symbol, completely different. All right. So, almost done with the chapter. One more thing. But unfortunately, maybe the harder thing to visualize, and one I want to go through the math with. So I hope I save myself enough time here on this last step. I want you to see what is going to be called here the Doppler effect here. It's not quite warmed up here, but one last step here, which really kind of fits into 2 steps, but I'll just call it 1 here because it's an extension of the Doppler effect. But Doppler noticed something that I want you to notice. I'll describe the Doppler effect this way. The Doppler effect is an observed. Now notice I use the word observed. It's an observed shift in frequency due to motion. Now let's see if I can explain that. And then of course run through some interesting math here for you. But like I said, it's worth going through the math so you'll understand the equation here. But this little diagram, this animation, is supposed to be this. If I were to take this sound source, so let me call this S, source, right here. Shows kind of a little speaker cone here. But as I hold this here, it's going back and forth 1,024. Let me just call it 1,000. So 1,000 times a second, it's producing a little concentration, right? A high pressure as it moves through. And that means this ear over here, as hopefully you saw in the animation, would be struck 1,000 times a second, right? That's the real frequency. The real frequency is 1,000. And so that's illustrated by this little flash of red. This is what the ear hears 1,000 times every second. Pulse, 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 pulse. What would happen if this observer, O, source, S, what if this observer moves towards the source? And if you kind of watch this play out, isn't the rate a little bit higher because you're moving into them? Wouldn't you pick up more than 1,000? And look at when you move away. What do you notice when you move away? It's less than 1,000. And this is why I write observed shift in frequency. The observer is going to pick up a different frequency than 1,000. Now, let me remind you, isn't this still vibrating at 1,000? So the real frequency is still 1,000. That hasn't changed. But the observed frequency has. The motion of the observer moving in or moving out does have an effect. Fair enough? It gets better. What if the observer is not moving, but the source. O, observer. S, source. You can see we're going to do some labeling with some equations, and we're going to have O's and S's. O's go for observer. S goes for source, right? And not sound. All right. So the source could be moving. Watch what happens when the source moves. As the source begins to move towards that ear, what do you notice here? See how they crunched up right there? We have a smaller wavelength. The motion reduced the wavelength. And as effect of that, boom, 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 you hear a higher frequency. And look what happens when the source is moving away from the ear. What do you get on this side? A larger wavelength, or a lower frequency. So again, the observed frequency is different because of the motion. And so we got to pay close attention to all four combinations. Did you catch that? We can have the observer moving towards the source. We can have the observer moving away from the source. We can have the source moving towards the observer, or we can have the source moving away from the observer. How do we handle that mathematically is the next big step here. But there will be a shift in that frequency. Notice that anytime they're coming together, whether it was the observer coming towards the source or the source coming towards the observer, what happened to the frequency? The frequency increased, right? And the opposite when they moved apart. Yeah.
So in case 4 when the source is moving, does that create an area of high pressure and low pressure? So the lower waves coming up together?
Well,
High pressure and higher areas of low pressure. So if we can look at the sound waves in the sense of differences in pressure, then wouldn't that be
well, when we have a sound wave, we always have, you're talking about, I think, right here.
right like this, so when we have an area of high pressure.
So these blue lines, say, represent high pressure. In between is low. High, low, high, low, high, low, high, low. And over here, high, low, high, low, high, low, high. Okay, so.
This is a relative effect.
Yeah, but this is a higher, this is.
There's a huge amount of pressure over there. It's just,
Yeah, it's not, yeah, right, it's not like it's a huge amount of pressure. It's this that it changes on a shorter scale. And so it goes from high to low in this distance, versus on the other side it goes from high to low over a bigger distance.
Would that be like noticeable? Like say you're looking at an average area of pressure, you know, say that in this area here seems to have a higher concentration, would probably have to do maybe speculative like pressures, and then you would notice that you're like measuring.
You would notice it if it got louder, if that's what you're after. I mean, that's what the pressure in waves is, the volume of it. Yeah. But I'm not sure just by moving that way, it actually has a greater intensity just because it moved. But what is happening is as it gets closer to you, it has less time to spread out. So something coming towards you is going to get louder. It's going to have a shift in frequency that's higher and get louder and louder as it gets closer. But I don't think it's the shift in frequency that is making it louder. It's the closeness of it that's getting louder. That's the important difference. Yeah.
What happens if the source accelerates through waves, all high pressure waves?
Oh, glad you asked. We're going to hopefully do that real quick here. But let me think if I can at least somewhat have you hear it before we do the math and before we do the next step, assuming we have time to do the next step. But if I take this crazy thing with a speaker on a long cord, turn it on, plug it in, turn it to a rate that you can hear. There's one. This is about 2,000. This is the source. You are the observer. Frequency, the real frequency is near 2,000, 2,153. What do you hear when it comes towards you? And away from you. Right? As it goes toward you, it should be higher. Goes away, it should be lower. Constant frequency. Shift in frequency, right? And so maybe you've heard, you know, Doppler shifted radar, right? This is a shift because of the movement. Maybe you've heard about astronomers looking out at galaxies and saying it is red shifted. What do they mean by that? Yeah, the frequency has shifted. It has shifted towards the red. It has shifted towards lower frequency. It tells them what? Moving away from him, right? Maybe you're driving down the freeway and the CHP officer fires the radar gun and it bounces off and it shifts in frequency, and it shifts a lot in frequency. Tells the officer what? Yeah, you're going really fast towards me and it's time for a ticket, right? So that's this idea of shifting of the frequency. So that shifting of the frequency can be measured, and it, of course, the amount of shift depends on how fast you're going. You can write it out this way. If we call S the source and the waves go out, and we call O the observer, let's talk about an observer that is moving with a velocity of VO for a moment. And if my observer is moving, it may move towards me or away from me, asking the question of what frequency would I perceive the observer. I'm going to put an F prime. Now, please don't mean derivative. That's not what I mean by F prime. F prime means just some other frequency. Some frequency that's not the real frequency. It's the observed frequency. What would I get? Well, maybe I'll come over to here. If there was no motion, wouldn't this be the calculation for frequency? Velocity of the wave divided by its wavelength? And so I would say this could be modified simply by saying the frequency that I, the observer, are going to pick up is a little bit higher if I'm moving towards by the speed I am moving towards. It is as if the waves are coming faster. Fair enough? And so that is how I would take into effect the movement of the observer. A slightly higher frequency. Why the minus sign? Why the plus sign? Why 2? So when would I use the plus sign? Yeah, and so if I am moving towards the source, I would have a plus sign. What if I'm moving away? Yeah, and so I will put toward and away next to the equation to say, let's use the upper sign if I am moving towards it, and let's use the minus sign if I am moving away. Oh, yeah.
Well, if you labeled an axis and said that a certain direction was positive or negative, which we should do for velocity, wouldn't that cover the plus or minus?
Not well. Because watch. If I call this the plus axis, right? Then which way is my wave moving? Positive, right? And if my source then moves negative, the negative velocity, I would have to write that as v minus a negative velocity. But then it would take care of it. But then I'd run into troubles when it's on this side. So it's better to do it this way. And so that's the standard. Actually, I've debated about changing it, but I've decided that since almost every book does it this way, it's kind of the standard. Whether it's better or not is debatable, but I know it's the standard. So it's kind of like, is gallons better than liters? We certainly haven't seemed to get away from gallons in this country. I do think liters is better, but because it's common, we're never getting away from gallons. Yeah. Not legally, how's that? That is part of the DMV code. And part of the FCC, you can't, is it possible? Sure. And I suppose, yeah, I mean, and essentially that's what you're doing on a B-2 bomber, right? You are sending back an electronic signal to cancel electronic signal, and hey, look, nothing's there.
So is it illegal to drive a B-2 down the freeway?
Yes. So, but the emission of radiation is, yeah, very illegal. Besides the fact of just messing with that. You know, it's going to mess with communications and other radio waves, and so.
But a car doesn't have a flat surface. Where do they know how the wave's getting reflected? If it gets reflected off the windshield, for example, it gets reflected up this way.
Oh, sure. So.
Point the radar at a specific corner.
Well, the radar is a very broad, so just pointing in the general direction covers everything. It hits the windshield, yes. In fact, the radar probably actually goes in through the windshield, doesn't reflect off. It is probably transmission. I'm not sure about that. But what they're after really is the reflection off the license plate. Your license plate is extremely reflective, and they'll aim it right at the reflective wave. In fact, California Highway Patrol has deliberately gone away. There's very few radars left. They have gone to a LiDAR system, which is the reflection of a laser. And those are much narrower because if you had two cars side by side and a radar and it comes back, you're not real sure which car it reflected off. And that's winnable in court then. Say, hey, it wasn't me, judge. But with the LiDAR system, that doesn't happen. The LiDAR systems, the beam's about this big, and the officer, has a nice sights on it to make sure they're hitting your license plate. And you can pinpoint which car of the three right next to each other.
So do you put material on your license plate to like...
Not legally. Same answer. All right, well, and in the few minutes we have left, let's look at the other option we have here. The other option is, what if the source was moving? And we're short on time in this picture, but maybe I should throw it back up there. What would it look like kind of midway in the stream here? No, didn't want to do that. Oh no. Okay, I wanted to just kind of stop it. I know if I click there. Okay, this is what I wanted to see. Right over here, I wanted to see how it's closer together. So, the other factor in here is the wavelength has changed, right? And the point I'm getting at is the numerator has been affected by the movement of the observer. It's the denominator now that it gets affected by the movement of the source. And so down here, if it is moving close together, I would say the wavelength has been contracted a little bit. And so I'm going to write this as, let me scoot it over, wavelength minus a little bit. Fair enough? Okay, except, what would happen if it is moving away? Yeah, then I would say the wavelength is bigger. So do you see the plus or minus, but do you see the different order? Do you see the minus is written up at top because it has to do with when you're moving together, toward. When do I use the plus sign? When they are moving away. Fair enough? All right, so you can see why I wanted to take a few minutes to derive this equation, because I have seen students struggle with this equation, when to use the plus, when to use the minus. Let's look closely at this real carefully here. This is the perceived frequency. This is what? What's this? Velocity of? The wave, right? This is the velocity of the sound. Do you see we got three velocities up here? And this is what I wanted to take to derive it. I wanted to keep clear what equations were happening here. We've got the speed of the wave, we've got the speed of the observer, and we've got the speed of the source. So far, we don't even have source listed up here, but after a couple of steps of math, we will. But this is the V of the wave. This is the V of the observer. The plus is for, the minus is for, the minus here is for, and the plus down here is away. And so look carefully. If one of them's stationary, that's easier than if they're both moving. But if they're both moving, we would have a shift because of the source, and we would have a shift because of the observer. A couple quick steps here. I can then replace this with plus or minus V naught. Down here, I am going to write this as frequency over wavelength times frequency. That's kind of boring. All I did was multiply top and bottom by f. But it's over here that I better just skip and get to the answer. So the final equation here is v of the wave, plus or minus, plus towards, minus away, and the observer. Oh, v, that's what this is going to come out to be, minus plus source times the frequency. And so there is what I wanted to get at, is what is the equation for the perceived frequency? There is a shift because of movement. Either one could be moving. The movement has a different effect. One shows up in the numerator, one shows up in the denominator, but that's the equation. And I guess the last thing I didn't get to was the shock wave. What happens if you go faster than the speed of sound? And in that case, I will just show you a quick video and leave it at that. Here is an object that is going faster than the speed of sound. First, it was going slower. Once it starts going faster, do you see how you get a superpositioning of the waves? Do you see how the waves that are made by the object all add up together in kind of a cone shape? I mean, this just looks like a V because it's two-dimensional, but if I had an airplane going faster than the speed of sound, as this, actually this is just Mach 1, all the waves would build up. You would have a superpositioning right here. This is where the high pressure would be. Terrible place for this plane to be because now it's got a big wall in front of it. So going Mach 1 is not a good situation. You see it best here. The next one is Mach 1 1/3. That is 1 1/3 times the speed of light, sound. See how the V begins to be created? You probably have seen this best with a boat. You ever seen a wake behind a boat? What that is meaning the boat is going faster than the speed of the water waves. Water waves are so slow, it doesn't take much for a boat to go faster than the speed of the water waves. And what will happen is all the waves it makes create a superpositioning, a V-shaped. And you see the same thing for anything going faster than the waves they're in. And so this being an airplane going faster is going to make a V shape. And so as the airplane comes by, it is constantly making these huge waves. Of course, I only hear it one time as it comes down and hits me. But please remember, that is not the moment it went faster than the speed of sound, as some people think. It is always producing those waves, just like a boat going through the water is always producing the waves. It only hits you once. But if it were to fly from Los Angeles to New York, it would be making the wave the whole distance, and it would break windows from Los Angeles to New York as it went there. And so, of course, we do not fly supersonic from Los Angeles to New York for just that reason. Perhaps someday we will develop and completely develop the supersonic transport, and instead we will leave LAX and go out of the atmosphere and come into New York in 20 minutes. But it will not be through the atmosphere, lest there be no people left in the United States. All right.